Okay, so I'm going to talk a little bit about rather small features in OpenMP, but useful ones. OpenMP, as we know, has been around for a long time, and we develop it, we maintain compatibility with previous versions, and along the way we introduce small changes, but you don't have to use these things. They're new advances in the way that you can use them, but they could potentially be useful in your codes. And so these probably account for 50 lines in the standard rather than being the 5,000 line things that a number of our people get obsessed with, and therefore it's very easy to miss them and to not notice that they're there. And so I'm just going to point out that we do have these new features, that they are potentially useful. And so there are two things that we're going to talk about. One is non-monotonic dynamic schedules, and one of the reasons you need to know about that is that they will become, well, they have become the default for dynamic schedules in OpenMP 5. And then the second one is hints that you can apply to synchronization constructs such as locks, critical sections, and in OpenMP 5 atomics. And those allow you to access hardware features on some vendors' hardware, in particular on Intel hardware, on IBM hardware, in ways that are very easy for you to put in, that don't make your code non-portable, and that potentially can have significant performance improvements, as we'll show. So we'll start with the lock hints, because those are to some extent more important. So this is the non-monotonic dynamic schedule, which sounds very long. And what is it actually about? We've had dynamic schedules forever. They were in OpenMP 1.0, I'm sure, and people use them, and we understand them. But we've changed we've clarified the semantics of the monotonic schedules in OpenMP 5. Well, in OpenMP 4.5 and in OpenMP 5. And so let's look at this piece of code here that we have on the right. We have a parallel region. We set a thread local variable, so this is inside the parallel region. Each thread has a copy of this variable, and it's called my. Then we run this schedule dynamic loop, handing out the iterations from 1 to n, and each thread looks to see whether the iteration it's got allocated is below the previous highest iteration that it had, and if so, it aborts. Otherwise, it updates its value of the maximum iteration it's seen. The question is, can that code abort? Does the standard allow that code to abort? That was not clear in OpenMP 4 because the way that the standard was written sort of suggested that what's happening in the implementation of the schedule dynamic is that there's one global counter which is being atomically incremented, and therefore there's no possible way that any thread can see an iteration that's lower than the one that it previously saw, because that global counter is incrementing and it's pulling values from the global counter. However, that was only, well, after a lot of political discussion in the standards group, we decided that that was not a specification, it was merely an example of how the standard could be implemented, and therefore that other implementations that allow that to abort are possible. That all sounds very abstract. Why would you care? Why does it make any difference? What are you going on about? Well, the reason it matters is that if you have a dynamic schedule implemented with that centralized atomic increment, and you have small amounts of work in the loop, you have a lot of contention on the cache line that holds that atomic variable, and you have many atomics attempting to operate on it at the same time, and that can perform very badly even on Intel machines. Therefore, what you want to be able to do is to use an alternative implementation in which you slice up the work between the threads initially. Each thread can then operate on its own chunk of work, just as it would have done if it were a static schedule, and then when it runs out of work, it can go to another thread and steal other iterations. And that way you remove all of the cost of those atomics. But in that schedule, obviously you can get this code would abort, because you could consider what happens if the thread that had the last set of iterations, that includes the highest one, executes all its iterations. It's executed the highest iteration in the whole set, and then it goes and steals an iteration from someone else. That's clearly going to be less than the highest one in the whole set, which would mean that code aborts. In OpenMP 4.5, we added qualifiers to the dynamic schedule, so you can say monotonic and non-monotonic, but we weren't actually clear about what it meant if you didn't say that. In OpenMP 5, the standard says that the unqualified dynamic schedule is non-monotonic, and therefore if your code is written in a way that relies on this property, it potentially will break when OpenMP 5 is implemented. So you need to know about that. Here's some measurements that I made showing the overhead there. So what we have a number of cores along the bottom here, up to 28 I think on the machine that I was using, and the cost of doing the scheduling depending on the amount of work that we do in each iteration. So if we only have 500 RDTSC ticks of work, which is a pretty small amount of time at a 2.7 gigahertz clock, then you get a cost of doing the scheduling like this, which is really quite depressing, because here we're seeing over 2,000 iterations of scheduling cost to execute 500 iterations of work, which doesn't seem like a good deal. Obviously, as we add more work, the contention on the lock decreases, and we come down to this line here, which is basically just the cost of the atomic in the first place. If you do static scheduling, that's the fastest of all, and it has no contention, and it gives you these red lines at the bottom. But if we do a non-monotonic dynamic schedule using the implementation that I was talking about, you get a performance like these green lines. I would rather have a performance like the green line than like the blue line, and that's what the standard now allows us to implement. So here are the advantages. It's significantly, the scheduling cost is significantly lower. Because the iteration distribution starts off being static, you get you're more likely, if there's only a little bit of load imbalance, to get good cache reuse than you would have done with the atomic-based, the symbol atomic increment-based dynamic schedule. And it handles the load imbalance better than a static schedule, which doesn't handle load imbalance at all. So it's not hard to do better than that. However, it's still slightly more expensive than a static schedule. So if a static schedule is appropriate, continue to use it. And by default, the static schedule is the schedule that most implementations give you if you don't specify anything at all. So we looked at this real code, MPAS Ocean, with some collaborators whose names were on the beginning of the slide. And it's an ocean system simulation. It's around 230,000 lines of Fortran. So it's not a huge code, but it's not a trivial code either. And it's a science code. It's a real code. It's not a benchmark. Using this workload, we ran one simulated day. It's an MPI and OpenMP code. And they already were using schedule of runtime for all of their loops. So doing this experiment was very easy. We just had to change the schedule in the environment variable. And here's the performance that we saw. So this is the performance versus a static schedule. So static schedule is 100%. It performs at this line here. And here's the performance if you use the two different dynamic schedules. So with a monotonic dynamic schedule, the performance is bad and gets worse and worse and worse. With the non-monotonic schedule, we actually do slightly better than static in a number of cases, and we're within spitting distance of static in the other cases. So there is clearly some amount of load imbalance in this code, and we're managing to to exploit that to go slightly faster. Now, this didn't, unfortunately, change the fact that for most of the MPAS cases, or even for this case, using many MPI processes and few OpenMP threads, and one OpenMP thread in each gave even higher performance. So it did change it from having one thread per MPI process to having 2 threads per MPI process. So we got some OpenMP parallelism to do better than the MPI parallelism. So what this is saying is that you can apply this in a real code and you can see a difference and you can see an advantage. So conclusions on this thing. You need to understand it because it's going to hit you whether you wanted it or not. The compilers are going to change, the runtimes are going to change, probably, and that may affect your code. It's possible that implementations may not bother to enable it even though they're allowed to, because if you think about it, the monotonic schedule could arise even though you said non-monotonic. So you can't tell by inspecting the set of iterations how they're handed out which schedule was actually used if it looks like a monotonic one. And so the implementer can argue, well, I'm doing non-monotonic and you just happen, every time you look, you just happen to see a monotonic one. Well, there's nothing I can do about that. That's just bad luck. And the reason that you might want to do that as a vendor is because that is safe. It's not going to break anyone's code. Exactly what we're going to do at Intel is still to be determined, but I think that we're moving in the direction of we will implement the default as non-monotonic, but we'll provide a non-standard chicken environment variable that you can set that says, just make everything monotonic again, please. It can provide useful performance, and the code changes that you need to make to enforce that by setting the by changing the schedule are relatively small in your code, and it's worth playing with. So use it. Okay? Anyone want to ask questions on that, or shall we move on to the other feature? Everyone's looking stunned. Okay, we'll move on to the next one. Synchronization hints. So here we're talking about a way for you to give more information to the OpenMP implementation, and in particular the OpenMP runtime, about the properties of the critical sections that you have in your code. You have a critical section in your code, either implemented with OpenMP lock, with an explicit OpenMP lock, with a pragma omp critical, or even atomic operations. And the way that happens, and the reason that's useful is that different implementations of that in the runtime have different performance properties, and therefore you can gain performance by using an appropriate implementation in the runtime. That's achieved with these hints that in OpenMP 4.5 had the name omp lock hint something because they were only applicable to locks and critical sections. In OpenMP 5 they changed their names to omp sync hint something or other, but the lock hint names are still there in case you're already using it. In which case, why are you listening to this presentation? So, why do I want to do this? Well, different lock implementations have very different performance properties. So the time to wake up on lock release to transfer the information about the fact that the lock is free to the next thread that is trying to claim the lock can be very different between locks, spin locks, or queuing locks. Similarly, the cost of contention, interference from threads that are waiting on threads that are still executing can be different. Fairness is different, and also the cost of entering the lock in the first place. So a Mellor-Crummy-Scott type queuing lock is fair, has low interference, but it's quite expensive. Any code path through it takes longer than a very simple spin lock. So if you have a highly uncontended lock, that's very rarely there are other two threads trying to enter the critical section. A spin lock will outperform the other lock, even though when you're under high contention, the Mellor-Crummy type queuing lock will perform better. Therefore, the runtime can't easily tell what the properties are of your critical section, so it's worth you telling it. And you can go and investigate and find that there are 8 different lock implementations in the LLVM runtime. Not that all of them would be useful here. It also enables, passing these hints also enables the use of advanced hardware features. So in particular, Intel processors have this feature called Transactional Synchronization Extensions, abbreviated to TSX. IBM have something similar in Power 8 and other processors. And that allows the hardware to speculate inside a critical region, and therefore to execute the critical region in more places than one, even though it's inside a critical region, and only abort that if there's actually a conflict that would cause you to be able to notice that the isolation was being broken. So how do you use them? Well, you change the place where you had a call to omp init lock to init lock with hint, and you add the hint. And that's it. You don't have to go and find every place in the code where you're doing set lock and unset lock. Just the initialization of the lock is all that you have to change. And similarly, you apply a hint to a critical statement. There are a few constraints there. It must have a name so that you know if there are many different lexical instances of that same critical section which you're trying to exclude. You need to name it so that they all know to use the same lock implementation. And they must all have the same lock implementation, so when you name it and put a hint on one of them, you need to name all the others the same and put a hint on them. The hints have no semantic implications at all. An implementation is entirely free to ignore them completely. So they're hints. You're saying, hey, runtime, I'm giving you more information, please use it. It can go, well, I don't care. I'm not going to bother. Which makes them very easy to implement and not contentious in the standards body, because people can't say you just caused me a lot of work. So mutual exclusion is still guaranteed, and an implementation can completely ignore them, but we hope it won't. So you're expressing properties of the lock and the critical section. Contended, you're expecting many threads to be waiting, so it's kind of suggesting to the runtime that maybe a fair queuing lock is a good thing to use. Uncontended, we don't expect many threads to be arriving here at the same time, so therefore use an unfair spin lock. And we can also hint to use speculation, which would be TSX on the Intel machines and IBM's hardware implementation, or to say don't ever use speculation. Right. Actually, it's unlikely that you would use speculation without being hinted to do that, but you can say both things. So TSX can give you the performance of a fine-grained reader-writer lock, but without you having to go in and implement everything and change your code to implement a fine-grained reader-writer lock. So the hardware enters a speculative execution state. It doesn't let any writes become globally visible, and it monitors the read and write sets inside the transaction to determine whether there are any conflicts, which it can do because of the cache coherency protocol. And then so the writes inside the transaction aren't seen until the transaction commits, and so if it aborts, those writes never happened, fine. No one can see them, they can't have caused a conflict. It has the property that in the Intel implementation that there are no forward progress guarantees. So you could potentially have two critical sections, speculative sections, and they each manage to invalidate each other all the time, and neither of them makes forward progress. That's not a very good property, but what it does mean, all that it means is that those of us who are implementing this in the runtime library have to ensure that we have a back-off strategy so that when we see too much contention, we go to some other lock which will guarantee forward progress. And that's all in the runtime, so you don't have to worry about it. That's my problem. So you could potentially detect that this is going on because you could read timestamps inside all the critical sections and see, hey, I'm in the, every thread's in the same critical section at the same time. But that's a pretty weird thing to be doing, and so I'm not too worried about that. So the example that we're using here is to say, okay, I've got some program. It's using a std unordered map, which is just a hash table, to map from an unsigned 32-bit integer to another unsigned 32-bit integer, and I want to use that inside an OpenMP code. Well, what I'm going to do is I'm going to build myself a locked hash class like this, and I put an lock in there, And when I initialize the lock, I initialize the lock. And then when I insert, I take the lock, I do the insertion, and I unset the lock. And similarly, when I do a lookup, I take the lock, I find the result, and I unset the lock. So this is a very simple way of wrapping up a function that isn't thread safe and making it thread safe so I can use it in OpenMP. And that's what the code without the red, orange, whatever color this is, would do. What I've also done here though is use the lock with hint, so I pass in a hint when I run the constructor of this, and I pass that into the init lock. And those changes in red are the only changes I had to make to do that. There are no changes. You notice no changes here where I'm setting and unsetting the lock. And when I run that code, so here I'm running this code on a similar machine with up on a Skylake machine with up to 28 cores, and I'm doing all the threads are doing lookups or insertions on random elements of a 10,000 entry array, entry hash, and I'm measuring 3 different proportions of that, all insertions, 50% of each, all lookups. I'm running 1 thread per core, and if I use the sort of default lock hint of uncontended, I get this performance in red, which is kind of what you'd expect. All of the threads are trying to be in the critical section at the same time. They can't be. Therefore, adding threads doesn't get me any performance improvement. How can it? All of the time is serialized. However, when I pass in the lock hint speculative, I get this very nice performance. The performance is increasing almost linearly as I add threads. And that's because without looking at it, inside the implementation of the hash table, you can speculate that what happens is it hashes the value, it goes and looks in that bucket. Maybe it changed from that bucket. And therefore, multiple threads actually are not accessing the same memory at the same time, even though they're protecting the integrity of the whole data structure. And therefore, using the speculative execution allows all the threads to be executing in that code inside the critical section, touching different buckets in the hash table without interfering with each other, and we get this nice performance improvement from that 2-line change. So that was really nice. This is really good. I can use this stuff for everything, can't I? So just to show that doesn't work, I tried another experiment where I'm trying to replace a set of atomics. So suppose I'm doing a set of contiguous atomics on an entry in an array, and I'm adding 1.0 to all these entries in the array. Can I instead of doing it with atomic, take a critical, take a lock and use a speculative lock? Seems like that might work too. Unfortunately, well, it works in one case more or less, but most of the time actually the atomics are still better. So this isn't a replacement for everything, but it is potentially a useful thing to look at. So they don't fix everything. They can be ignored, so you're not going to hurt your code's portability by putting them in, and where they work, they can give you significant gains, as we saw. So consider using them. It's very easy, and you potentially can have big gains. And so the overall conclusions of the whole talk are OpenMP is evolving, and is evolving in ways which are actually quite small but are useful, and it's worth knowing about those things. And these small changes can be quite easy to apply to your code. They're not things that require you to restructure your code or go and touch every line in your code or any of these things. So think of using them. And I have to acknowledge my collaborators who did the work on MPAS-O. And since I'm from Intel, I have to give you detailed test configuration information about the machines which were used when we did the testing, exactly the properties of the compilers and so on, so that you can go and replicate this. Well, you can't replicate the 10th of September 2018, but you can replicate the rest of this yourself and validate or send me an email and tell me I'm an idiot and I made some horrible mistake. And I have to show you a legal disclaimer that says this guy works from Intel, he used the Intel compilers. The Intel compilers may not optimize as well for other people's processors as they do for Intel. Thank you very much.